Hello, I will be going over number 17 on homework number 2. And in the problem, it states that the lowest note on a grand piano has a frequency of 27.5 hertz. The entire string is 2 meters long and has a mass of 400 grams. The vibrating section of the string is 1.9 meters long. What tension is needed to tune this string properly? So, the first thing I like to do is to make a list of my knowns and unknowns. And so, it says that we have a frequency of 27.5 hertz. And that is our lowest note, or otherwise known as the fundamental frequency. And so we have a fundamental frequency of 27.5 hertz. And keep in mind, this is a standing wave, and so that will be important later on. Standing wave. So, and in addition, it says that the entire string is 2 meters long with a mass of 400 grams. Or 0.4 kilograms. I put it in kilograms because we're finding the tension, which is in newtons or kilograms meters per second squared. And it also says that the vibrating section of the string is 1.9 meters long, and so I'll denote that as L sub v is equal to 1.9 meters. And we need to find tension. And so if you recall that velocity is equal to the root of tension of the tension on a string over the linear density. And so we can find tension by isolating it. So sorry about that. So we can square both sides to get v squared is equal to tension over linear density. And we can multiply linear density to the other side to give us density times velocity squared is equal to tension. And so we know that we need to find values for these two. And so what we'll do is find mu. And so we know mu is equal to mass over length. And so this length is total length, because the linear density corresponds to the density of the entire string. And so we'll use 0.4 kilograms as the mass and 2 meters for the length, which gives us 0.2 kilograms per meter for mu. Right here. So we now have mu. We just need to find velocity. And so we're given the fundamental frequency. And so if you recall also that the fundamental frequency is equal to velocity over 2 times length. And so we can isolate v to get 2 times length times the fundamental frequency to equal to velocity. And so since we now have mu and we now have velocity, we can plug these values into the tension equation. And so first I will plug in the velocity to get mu times 2 length fundamental frequency squared equal to tension. Once we have this, we can now plug in our mu, which is 0.2 kilograms per meter times 2 times length of the vibrating section, because it's for the vibrating section because we're using the fundamental frequency equation, which is for a standing wave. And it says that the vibrating section is 1.9 meters long. So that is the section where the wave will be. And so we have 2 times the length of the vibrating section, or L sub v, is 1.9 meters, times the fundamental frequency, 27.5 hertz, quantity squared. So I'm going to move this over here so we have some more room. Quantity squared, because this right here, can't forget that square. So if you plug this in, after rounding, you'll end up getting 2,180 newtons. If you check the units, they all cancel out and give you kilograms meters per second squared. So, and this is the tension you need.